Back to COSC 2325. This is part 1 of chapter 5. We're going to start talking about procedures. So how to create functions and methods in assembly language. We're going to have this video that's going to talk about stack operations. We're going to have a video that will go over how to define and use procedures. And then we'll have a video to talk about just the Irvine 32 library. Okay, so the first thing that we're going to get into is stack operations. The stack that we're talking about is the runtime stack. The operations that we're going to be doing on the runtime stack are push pop instructions. And when we say the runtime stack, we mean the stack that is used by functions, when you call functions, and local variables and parameters are kept on the stack along with the address of where to return to after you're done calling that stack. Here is a picture of how you can visualize the stack. So imagine a stack of plates, a stack of very heavy plates, like in a lunchroom. So these heavy plates made out of ceramic. So when you stack these plates, you don't ever want to grab a plate from the bottom or from the middle because they're so heavy. So if you grab something from the middle, the bottom, the top plates might actually topple over or break or crash into each other. So when you take the plates off the stack, you take them from the top. So the very last plate that you put on the stack is the first plate that you take off the stack. So in this example, in this picture that you see here, this is the first plate that we put on the stack. This number 10 is the last plate that we put on the stack. This 10 will be the very first one that we get off the stack. When we talk about a stack, you want to think of it like an array, and you have this chunk of memory that you've allocated. We specifically allocated when you write your assembly program at the top, it says stack 4096. That's how many bytes have been allocated for your stack. And what we're going to put on the stack, what's going to be inside each, let's say, element of the array, is either going to be values like numbers, characters, strings, or you can put addresses in a stack. This stack structure, we call it a last in, first out structure. So last in, this is the last in. That's the first thing that comes out of the stack. Okay. The runtime stack is managed by the central processing unit. So if you've taken a data structures class, you've talked about stacks that you create as a programmer. These are not those stacks. Same concept, but different stack. This stack is it's managed by the CPU and specifically for procedures, for those functions. The stack uses two registers, so we have a stack segment and a stack pointer. We're going to be looking at the stack pointer a lot. So the stack pointer always starts before you put something on the stack. It's always right above where your stack begins, where that memory has been allocated. And then once you put something onto the stack, like the 6 that's been put onto the stack pointer, which is just a register that holds an address. So this ESP, what it's holding this address right here. And so this ESP is pointing to the 6. So one of the operations that we can do to put things on the stack is a push operation. When we do a push operation, you can do two things. You can push an immediate value. So you can say push and then an immediate value of 5. Like here they pushed a 6. So let's put a 6 there. Or instead of putting an immediate value, you can put a register here. Now, if you put a register, that register needs to be either a 16-bit register or a 32-bit register. It cannot be 8-bit register. So you can push 2 bytes or 4 bytes. In this example, they've pushed a 6. So it says a 32-bit push operation decrements the stack pointer by 4 and copies a value into the location pointed to by the stack pointer. So the first thing that's going to happen when you do a push, let's say that we push 6. If we push this 6, it's going to be a 32-bit value. It's going to first decrement the stack pointer. So the stack pointer starts here. And our stack is actually going to grow downwards. So the thing at the top of this drawing is actually going to be the bottom of the stack. So our stack is going to grow downwards. We're going to subtract. Well, we're not going to subtract. The push operation itself does the subtraction. So if you push this 6, 4 is subtracted from the top of the stack, and we start at this value, 1000, and ESP points to 1000, and the 6 gets copied. If we do another push, we subtract 4 bytes from 1000, which gets us to FFC. Remember, this is 1000 hex. So if you're subtracting 1000 hex, you're basically borrowing. So this is 6, this 1 represents 16. So this is 16 here, because you just borrowed 16. And then this 0 is going to borrow 16. So this becomes 15. This becomes 16. This 0 is going to borrow. So this is 15. And now this is 16. 16 minus 4 is 12, which is C. And then 15 minus 0 is F. 15 minus 0 is F, because F is 15. So we subtracted 4 bytes from the 1000 hex. ESP now points to FFC, and now this value got pushed onto the stack. So this is like saying push A5. So we call push A5. First, there's a subtraction done, and then the value gets moved in that order. Here's the same stack with 2 more pushes. So they pushed a 1, they pushed a 2. Once they push the 2, the ESP pointer is pointing to the 2. Remember what ESP holds. ESP is a register. We're going to be able to see that register, and that register is going to hold an address. And it's going to hold the address of where this 2 can be found on the stack, which is going to be the very last value. ESP will always hold the address of the last value that got pushed onto the stack. Again, the stack grows downward, so the area below ESP is always available. This area is always available, unless the stack has overflowed. We can make the stack overflow by creating like a recursive call to a method, to a procedure, and not exit out of that recursive call, and then we can overflow that stack. So now we're gonna look at the pop operation. So once you put stuff on the stack, okay, so it's just a place in memory. It's holding values for you temporarily. You can pop those values off the stack, but remember that when you pop them off the stack, it's going to start at the bottom of the stack. So in this case, this is the stack again, just like we saw it a minute ago. If I do a pop, it will pop the 2 off the stack, and it's going to put it into a register or wherever it is that I want to pop it into, like a memory location. So if I say pop the 2 into EAX, then that 2 will get popped into this register right here, EAX. It'll get placed into EAX. Now, when you do a pop, the first thing that happens is the 2 gets copied to the register that you're moving it to. Since we popped EAX, we're going to subtract 4 from this address. So we subtract 4 from ESP, and then ESP is now here. And that's what's happening here. So first the value gets copied into the register, and then ESP gets moved back. I'm sorry, not subtracting, we add 4, because now we're popping. So when you pop, you add the 4 to get to FF8, okay? So push subtracts, pop adds. How much do you know to subtract and add? It depends on what you're pushing and popping. So if you do a push, again, and you push AX, like whatever's in AX, then you're going to subtract 2 bytes. If you pop into AX, you add 2 bytes. That's what it says. That's what this says right here. So you can read that, and it's exactly what I just said. So when we do a push and a pop, these are the rules. You can push either a register or a memory location that's 16 bits, a register or memory location that's 32 bits, or an immediate value. So an immediate value will get pushed as 32 bits. So like a 5 will get pushed as 7 zeros and a 5, which is going to be 32 bits. And then when you do a pop, you can pop into a register or a memory, and it can be 16 or 32 bits. Of course, we cannot pop into an immediate value because it's impossible to put something into a number that doesn't have a memory location. Remember that registers are memory M would be like a variable that you create. So this would be like AX. This would be like var1 defined as a word. This would be EAX example, var1 defined as double word. Using push and pop example. So in this example, what we're looking at is we're looking at 3 registers that are going to get pushed to the stack, and then we're going to pop the values from the stack. It is important that you know that when you push something to the stack to restore the values, you have to pop them in opposite order. So you push ESI, ECX, EBX, and then you pop into EBX. See, that's the last one onto the stack. This is the first one you pop. This one got pushed second. That's the second one you pop. This one got pushed first. That's the last one you pop. So let's take a look and see what's happening here. So let's say that ESI has a value of 4 to start with, and this has a value of 1, and this has a value of 6. I'm just getting some random values, and let's say that those are in there. So when we do push ESI, I'm going to draw my stack over here. I'm going to push ESI here. So I push the 4 there. Well, first, my ESP, my stack pointer got decreased. It got moved here. This is where ESP got moved. And then the 4 got pushed onto the stack. Then when I push ECX, ESP gets moved here. ESP, and then a 1 gets written there. Then when I push EBX, the 6, now ESP moves down. It's no longer there, it's here. And then the 6 gets moved into the stack. So the ESP pointer is here at the 6. This is the top of my stack. I'm gonna put here top, because that's the last number that got put on the stack. Then here, so I pushed all these onto the stack. They're saved on the stack. They're saved, those values are saved. So then here what they've done is they just rewrote those values. They changed the values of ESI, ECX, EBX. So they set ESI to the offset of double word val. So it's some memory location. The offset is some memory location. So ESI will have some memory location. I'm going to make up a memory location, and I'm just going to say that ECI holds this memory location. 1, 1, 1. Okay. And then ECX holds the length of double word val. Well, I don't know that length. I'm going to make up a length. I'm going to say it's 100 elements. And then I definitely know the type of the double word is 4 bytes. So I'm going to put 4 right here for EBX. So these values, they went away. They got replaced with these. But that's okay because I have them saved over here on the stack. So now I'm going to restore. By the way, this call dump memory is a library, comes from a library called the Irvine library that we haven't talked about yet. So don't put that in your program if you want to test this out, because we haven't worked with the Irvine library, but I will show it to you later when we worked with the Irvine library in part 3 of these videos. So when we pop EBX, this 6 right here gets popped. So what happens first is the 6 gets moved to the EBX. So here's EBX. Okay, so see, it's restored back to the 6. And then the pointer, boom, 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 pointer goes back up. So let me erase this. Pointer goes back here. Now notice I did not erase the 6. The 6 doesn't go away. The 6 is still in memory. I'm not pointing to it anymore. So it's sort of cleared, but it's not, because I don't actually clear it off the memory stack. I just point to the 1 now. So since I'm pointing to the 1, there's a pop here. It says pop into ECX. So this 1, since that's where the ESP is, pop says take the value that ESP points to and move it to there. So now ESP moves here. It's pointing to the 4. And the last pop, that 4, gets popped and it replaces that. So this 3 lines restored my registers, but you just have to remember to do it in reverse order. So we'll do ESI, last thing that you pushed was EBX. First thing you pop is EBX. Okay. And we're going to do an example at the end of this. Okay, here is an example of using the stack for nested loops. So when you have a nested loop, let's say a nested loop in C++ or Java, you have a for loop and you have another for loop inside that for loop. Oops. And in this for loop, let's say that this for loop, you have something like x equals 1, x is less than or equal to 5, x plus plus. So this outer loop, this is the outer loop, iterates 5 times. The inner loop, let's say that it iterates from 1 to 3, so 3 times. And this is y here. So this will iterate 3 times. So we know that what happens with loops is that, and let's say this has something here, some statement. This inner loop, when x is 1, we know that the inner loop, which is y, will go 1, 2, 3, 1, 2, 3. Then when x changes to 2, the inner loop will go 1, 2, 3. And when x is 3, the inner loop will go 1, 2, 3, etc. So this inner loop just keeps, right, iterating 3 times. This one only changes once. This one goes 3 times. So this code is basically this here, except their outer loop is 100 and their inner loop is 20. It's pretty large. The way that loops work, just as a review, they use the ECX register. So at the end of the loop here, at the end here, ECX gets decreased by 1 always. And then it compares, is ECX equal to 0? And if it's not equal to 0, it loops again. So the way that this example works is that ECX gets assigned 100. We push, we go inside. This is the inner loop right here, by the way, inner loop. And then the outer loop, we'll pick a red here. This is the outer loop. L1 is the outer loop. So we moved 100 to ECX. We push the 100 to the stack. So now we're saving that value. We change ECX to 20. So I'm going to put ECX over here. ECX starts at 100. We push it onto the stack. Changed it to 20 right here. Now we go in the loop. This loop is going to iterate 20 times. So it basically, here it decreases ECX to 19, 18, 17, 16, blah, 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 until it gets to 0. Once it gets to 0, it stops. And it does this instruction, pop ECX. So it pops the 100 back to ECX. And then this instruction decreases that 100 to 99. We go back up. We push ECX to the stack. This had already gotten popped off, so we're back here. We move the 20 back to ECX, and we do the inner loop 20 more times. We pop ECX back. We pop the 99. ECX gets decreased to 98. We push the 98 onto the stack. 98. And so it keeps doing that until this 98, this this thing here becomes 0. Once it, actually, once it becomes a 1. Once it's a 1, once ECX is 1 here, then this will decrease it to 0, and it'll say, is ECX equal to 0? And it's true, so it stops the loop. So right now what I want to do is do this exercise using online GDB. I mean, not online GDB, gosh, what class am I in? Visual Studio. So I want to make sure that you also type this in and run it. And what you're going to be looking at is ECX and the ES and the stack pointer, which is the ESP register. Okay. So right here, we're going to first define the outer loop, sorry. L1 is just a label. You could call this label anything like LA1, whatever. So how about we call it outer loop? Outer loop. And then this would be outer loop. Kind of confusing, but so you've got a label, and then I typed that in wrong. So then we have the keyword loop first, and then the name of our label. So it says loop to outer loop. There we go. Or how about we just call it outer? That's the outer loop, and then we'll create an inner loop. So we'll call this in loop, loop in. So I need to set my ECX for my outer loop. Like, what is my outer loop value going to contain? So at the beginning, I'm going to set ECX to, so I want to make my outer loop be 5, like that example that for loop, the C++ for loop. So the outer loop is going to iterate 5 times. And then the inner loop is going to iterate, I'm going to make the inner loop iterate 3 times, like my example. And inside the loop, I'm not going to do anything crazy. I'm just going to move into EAX the value of 0 or 1. Because to make this work, I have to have 1 instruction in here. So I just made up an instruction just to make this loop work, okay? So this is my outer loop, which starts with a 5. Before I change the inner loop value to a 3, I need to save it in my stack. So I'm going to push ECX to the stack. Now that I pushed it, I have saved outer loop value. And then here, sorry, I'm thinking about the spelling of outer. I'm not the best speller. So, but I do like to, since English is my second language, I always doubt myself on my spelling. Okay, no, I had it correctly. Okay. Otter, I think would be like 2 T's. All right, so here I saved the outer loop value. So I pushed it, I pushed ECX. Now that I save it, now I can change it. Now it's going to go inside the loop, and it's going to loop it. This loop instruction here is going to decrease ECX. Decreases ECX by 1. And once it decreases it, then it compares, and it says, is ECX equal to 0? So decrease, compares. Now, once I'm done with this inner loop and this inner loop iterates 3 times, then I'm ready to put back this 5, restore. So I'm going to pop into ECX. And what is popping is the 5 the first time. And then this loop outer is going to decrease ECX, which right now has the 5 by 1, and compares. Is ECX equal to 0? So because assembly uses ECX only for its loops, we've got to save those values. So I'm going to go ahead and put a breakpoint and just step through it. So let's put a breakpoint. Well, before I put a breakpoint, I'm going to run it to make sure I haven't made any errors, which I did. So let's take a look at the errors. So it says that I have that in isn't a problem. So it says that it's an instruction. So I don't know what kind of instruction that is. So I'll choose something else like in loop. I'll call it in loop. That's a keyword. In is a keyword. I don't know what keyword. I don't know what it does. Okay. So everything ran okay. I'm going to take this off and I'm going to put right here. I'm going to put my break before this move into ECX. So I'm going to look at ECX and I'm going to look at the stack pointer right here. I'm going to see that changing. So first 5 is going to get moved to ECX. Here's my ECX. It changes to 5. That's my outer loop. I'm going to push ECX into the stack pointer. So my stack into my stack. So my stack pointer should change. So that is the address. That is the address pointing into the stack of where that 5 is. Okay. Now I'm going to move 3 to ECX. I'm going to see that change to 3. And now my inner loop is going to iterate 3 times. Okay, so watch as I click step into, I want you to watch this yellow arrow, and it's going to move through here 3 times. So I move 1 into EAX. ECX is going to get decreased. Watch ECX get decreased to 2. See right there. 2 is not equal to 0. So I'll go back in here. Moves 1 into EAX. ECX got decreased to 1. Loop is the one that decreased it. Back in. Decrease ECX to 0 now. See how it's 0. And at that point, when it decreased it to 0, it says is 0 equal to 0? Yes. So it stops this loop here. Now we're going to pop ECX. So ECX is going to get restored to this 5, which is the outer loop value. There's ECX is 5. And then we're going to go 5 is not equal to 0. So we're going to go back up. I just did something I did. Sorry. Let me get it back to where the 5. So there's a 5. So decrease ECX by 1. There we are. So ECX is now 4. Now I got to save that 4. Got to push it to the stack. I've got to change ECX to 3 for my inner loop. My inner loop will iterate 3 times. 1. Keep exiting. My goodness. 1, 2, 3. So ECX is 0, that's for the inner loop. Restore to 4, and then go back up. 4 + 4 is not equal to 0, and start again until this ECX for my outer loop is a 0. 2, 3. ECX, the outer loop is a 2. This is where it's going to stop. So right now, ECX is a 1. This is going to decrease it to 0. Compare and stop. There we go. Okay, so type this in, run it, and make sure you understand it. The last thing that we're going to look at is these related instructions, push FD and pop FD. This, you can just type this in like this into assembly, this instruction, and it's going to save the ePlex register. Maybe at some point you have the flags and you do some addition and subtraction, and you don't want those flags to get messed up between those addition and subtractions. You want to restore them. You would use the push FD and pop FD, and then push AD and pop AD. These instructions will push all the registers, all the general purpose registers. 1, 2, 3, 4, 8 for general purpose registers will get pushed to the stack so that you can save them there, do some instructions, pop them, and then pop them back to restore. So if the problem ever says to save all the general purpose registers, you use push AD. Restore all the general purpose registers, use pop AD. Now you could do push, 1, 2, 3, 4, 5, 6, 7, 8 instructions, and then do 8 pop instructions, but that's a lot of work. Now, when you push, it pushes it in this order: A, C, D, B, E, S, B, E, B, P, E, S, I, E, D, I. So that's the order that it does it, and then it pushes it backwards. There's also a push A and a push and a pop A that we're not going to be using. It's for 16-bit registers, but it's only when you do 16-bit programming. So it would push like AX, CX, DX onto the stack, and you could pop them, but we just do the AD, push and pop AD. The other thing I wanted to say is sometimes and we'll look at this later, you may not want to push all the registers onto the stack. You may want to keep the change that you made to one of the registers and not restore them. So then we wouldn't have push AD available, but we'll look at that later. So what we're going to do in this example is we're going to write a program that assigns integer values to these registers. You're going to use push AD to push the general purpose registers onto the stack. You're going to use a loop to pop each register from the stack and display it on the screen. So instead of displaying it on the screen, we're not going to display it on the screen because we have not used the Irvine library yet, but we're just going to pop them into each register, and then we're going to just look at them in the registers, okay? Later on, you could look at it on the screen. And you're actually going to be turning in this assignment here. I'm just going to copy this. We'll put it here in the comments section so I can remember what I'm doing. So the first step, it says, assign integer values to these. You can do this on your own if you feel like you're able, or you can just do it with me. So we're gonna do a bunch of move statements. Move into EAX. I'm gonna put a 1. EBX. So means CX 3 DX 4. So A, B, C, D, and then ESI and EDI. Okay, so it says assign integer values to those. These are integer values. 1, 2, 3, 4, 5, 6. A, B, C, D, ESI, EDI. Use push AD to push the general purpose register onto the stack. Okay, so we're gonna do push AD. That pushes everything onto the stack. Now I'm gonna go back to this slide and look at the order that push AD works. So here's the order. It's important. The order here. So it pushed EAX first, then it pushed, I'm sorry, yes, it pushed ECX, then EDX, EBX, like that in this order. So notice that EBX is not second. Okay. So it says using a loop, your program should pop each integer from the stack and display it on the screen. So instead of doing that, because we can't display it on the screen. First of all, if I wanted to pop these in the right order, I would do a pop. I would pop. Let's take a look here. Put all that up. So if I wanted to, after I push them, if I want to pop them, I would have to pop EDI first. I would have to go like pop into EDI and then pop. It's not what it's asking me to do, but I just wanted to show you pop EBP. So if you do a pop AD, this is basically what's happening. Pop AD. It pops EDI first, and then pops into ESI, then pops EBP. Because the last one that got pushed is the first one that gets popped. So that's what a pop AD does. Now this is asking us to just use a loop and then pop each one. So why don't we just use a loop and pop it into just a register and look at it as we pop each one. So we're gonna put a loop, call it L1, L1. And we're going to pop, and let's just pop it into EAX. So how many times should this loop iterate? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. So they listed 8 registers. Here we only filled 6, but that's okay. We didn't fill EBP. Oh, I know why. This is the stack pointer. This is the base pointer. So we didn't put any values there because those are automatically generated. And we haven't talked about the base pointer. So we're going to pop these values into EAX. So what we'll see is we'll see a 6 first. Let's write down what we're going to see. So we're going to see a 6 first because that's going to get popped. Then ESI will see a 5. Then we're going to see some address and some address. Address. Then we're going to see EBX, which is a 2. Then we're going to see EDX, which is a 4. Then we're going to see ECX, which is a 3. And EAX, which is a 1. Like that. So I'm going to put a break and then run it. And then we're going to watch as we pop each one of these. So we just moved EAX, moved the 2. We're going to move the 2 into EBX, move the 3 into ECX, 4, 5, 6. Okay, so we have 1, 2, 3, 4, 5, 6, and then EBP has this address 009C. It ends in 64. ESI has a 5. And ESP has this address that ends in 58. So then we're going to do a push ID, so that pushes all the values onto the stack. And then we're going to start popping the values. Oh, the one thing I forgot to do was set ECX. So we actually need to set ECX. Right now, ECX is 3, so it's only going to pop 1, 2, 3 values. That's okay. Let's watch those 3. All right. So the first one, it popped the 6, which is what I have here. So it popped the 6 in there. Then it's going to pop the 5. So there's a 5 right there. And then it's going to pop the address that we saw in earlier, which I can't remember what it was. It was this one, ending in 64. And I was using the ECX register. It had a 3, so it's just going to iterate 3 times. So the one thing I forgot to do was to move into ECX. So if I want to see all these, I would have to, I'll go to 1, 2, 3, 4, 5, 6, 7, 8. I would have to move 8. And then I could see all of them. So now I have 38. And what am I looking for? Stack pointer, 2D. Okay. So the first time I see 6, then 5, then an address, then another address, then a 2, then a 4, then a 3, then a 1, and my loop stops. So this loop just goes and it pops everything that's on the stack, which is these 8 registers. Make sure you get this typed in, and then what you're going to turn in, it's just showing that your program ran. So if you take this break off, you just run it, and it shows that down here. So the console actually shows here that you exited with code 0, and then it doesn't have any errors here. Can't find my window that shows. Okay, so that's what you're going to turn in. And then for and the very last slide here in this section is reversing a string example. And this example, I have it in Canvas, reversing a string. So pull up that program. And I also included the video that comes with the book. So your author did a video on how this example works. So I want you to look at his video since it's already done, and he does a wonderful job. Shows you how to reverse a string. Okay. And then I'll see you in part 2 of chapter 5.